Hello, everyone. My name is Joe Majdalani, and the purpose of this presentation is to tell you about the type of research that my group does here at Auburn. So since 2013, I've joined Auburn and established the Advanced Propulsion Research Lab. This lab is devoted to aerodynamics and propulsion. It consists of a group of graduate students that focus on the theoretical and computational analysis of advanced chemical propulsion systems. Most of the time we work on swirl-driven liquid and hybrid rocket engines and also solid rocket motors that have innovative features in them. And we've even studied nuclear thermal propulsion systems. Our objectives are to improve the performance and safety of combustors and rocket engines by leveraging swirl as a component, incorporating swirl into our flow field structure, and also by promoting safety by ensuring a stable rocket system. And by stability, we are referring to combustion and acoustic stability. So one highlight of our research has been the fact that the fourth edition of Viscous Fluid Flow, a well-known textbook that's used all over the world in over 1,000 universities, used at all of these universities to teach boundary layer theory and viscous flow theory. It has featured a wall-bounded cyclonic chamber on its cover, front cover and back cover. We're very excited about that since this is the first propulsion system that is featured on the cover of a fluid mechanics textbook that is widely used. Our sponsors over time have consisted of a variety of institutions and companies. The most prominent of those have been the National Science Foundation, NASA, Orbitech, which later became SNC, and Research in Flight, which has been developed by one of my good colleagues, Dr. Roy Hartfield. Our two focus areas of concentration have been the modeling of swirl-driven cyclonic flow fields and also the modeling of wave propagation and acoustic instability in chemical propulsion systems. For the swirl-driven cyclonic chambers, these are concepts that have been pioneered by Orbitech, now SNC, that involve the introduction of an oxidizer into a liquid rocket chamber tangentially to the inner circumference, a very unconventional design, unlike most liquid rocket engines that introduce the fuel and the oxidizer at the head end of the chamber. In this case, the oxidizer is introduced at the bottom of the chamber, just upstream of the nozzle. The flow field or the incoming stream of oxidizer ends up swirling around, traversing the length of the chamber twice before exiting. And when nearing the top, the fuel is added to it, combustion is promoted, and the products end up coursing their way and expanding through the nozzle. However, while swirling around, the oxidizer, which is essentially introduced at the bottom of the chamber, ends up creating a thermal blanket, sort of acting as a film coolant along the side walls, thus preventing the combustion products from contacting the walls and providing for very effective convective film cooling. We've been part of the developmental efforts of this engine since 1995. We've worked on a number of simulation studies that involve non-reactive flow simulations of this engine that help to describe the flow field structure. We've also been part of a number of reactive flow simulations with a variety of fuel oxidizer mixtures, including methane, hydrogen, propane, etc. And this is an illustration of the results we obtain using a simple model of propane oxygen combustion, which demonstrates that despite the very high temperatures in the core region that near the adiabatic flame temperature of 3,500 Kelvin, the regions near the wall remain at much lower temperatures, again, due to this effective film cooling. We look at a top view and an isometric view that also help to corroborate this behavior where the annular region is very nicely cooled while the core region remains very hot. Again, the cooling of the walls enables us to get away with using lighter materials and having greater flexibility in selecting materials. Also, it precludes the need to use cooling jackets, thus leading to a much lower weight overall engine. Such engines are ideal for upper stage applications. Again, some additional isometric views of the engine that help to demonstrate that at every elevation, the engine is very nicely cooled. We are also able to capture and pinpoint the species concentrations and distributions throughout the chamber, thus helping us to corroborate how the oxidizer that is introduced is going to evolve with a bit of the oxidizer also coating the inner side of the nozzle, thus leading to the cooling of the nozzle on the inside. We've looked at a number of arrangements for the fuel injectors, injectors that are co-swirling or counter-swirling, some that are radial, some that are coaxial, and by running different simulation studies, we were able to eliminate those that are not advantageous and select the more optimal or the most optimal configurations that will lead to the best efficiency while mitigating the formation of any kind of hotspots along the walls. The engine itself has been highly celebrated. It's been featured in Aerospace America in a number of issues, also in the Spacetime magazine, or it's been called the Tame Tornado. It's also been heavily funded. This is $25 million earmarked by the Air Force to further develop this engine. Also, NASA has invested quite a bit, and the Army. We've been fortunate again to be part of the developmental efforts on the academic side. This is an illustration of the engine that's been built and back in 2012 and flown in the Mojave Desert very successfully. So let's watch. Notice that this is using an relatively cooled graphite nozzle. The engine was very stable and achieved all of its performance targets. Shortly thereafter, Sierra Nevada Corporation, that was looking for a very robust engine, ended up buying out Orbitech. We've been very privileged to have worked with Orbitech since 1995, and currently we continue to work for SNC on the further advancement of these technologies in a variety of more advanced concepts, and also carry out the theoretical analyses of these engines side by side with our computational efforts. Also, another important concentration for our team has been on the development of mathematical models for wave propagation, in this case, the vortically-acoustic wave coupling that can take place in liquid rocket engines, in this case, those that mimic liquid rocket engines, such as those leading to the destruction of the injector faceplate on the F1 engine as part of the Saturn V. This study helped to explain how the coupling can occur, leading to the doubling of the amplitudes and leading to significant damage to the injector faceplates. Several papers have been published as a result of these efforts, leading to the Abe Zaram Distinguished Medallion in Astronautics that was received by one of my happy grad students, Charles Haddad, who's now moved to Houston, working for Schlumberger. Another important focus area for us has been the modeling and simulation of hemispherically bounded cyclonic flow fields, such as those that are ideally suited for use in upper stage applications. Langston Williams has been leading this effort in CFD modeling and also in the development of analytical solutions. Not only has he been able to obtain one analytical solution, but 4 exact solutions to the Navier-Stokes equations with no viscosity, therefore the Euler equations, and his work has been recognized also with the Abe Zaram Medallion in Astronautics that he received in 2018, and he was selected to represent the United States at the International Astronautical Congress that took place in Australia that year. So this is an example of the things we like to work on, besides the computational simulations, much of which we cannot publish because they are proprietary, we can only provide to our sponsors, but the analytical solutions that we obtain are quite nice. This is an example of 4 exact analytical solutions for the stream function, from which all the other properties can be easily derived. We've also developed comparable solutions for conical cyclones with different conical half angles. We've also, these conical cyclones are relevant to the flow separation industry, where they use conical cyclones for dedusting and for filtration, and also for isotope separation. But really, our history with cyclonic flows goes back to 95, 96, where I was commissioned by Orbitech to develop a phase 2 proposal to help advance what was known at the time by NASA as the vortex injection hybrid rocket engine. So my journey with Orbitech and now SNC started back then. The results were compelling. Amongst them, we were able to obtain exact solutions to the Navier-Stokes equations that were obtained almost exactly. I said exact, but they were rather asymptotic, but carrying a very small truncation error, rendering them almost exact, with, again, results that mimic the CFD simulations quite well. The analytical solution here shown on the left almost mirrors the CFD results. We also ended up uncovering families of helical flow solutions that apply to wall-bounded cyclonic configurations that we've coined complex lamellar, linear and nonlinear Beltramian, and generalized Beltramian, that exhibited very unique properties that also were published in top-tier journals. And when we talk about a cyclonic flow field, it's important to understand 2 properties that differentiate one cyclone from another. One of them is the mental location. The second one is the location of the peak tangential or Schur velocity in the chamber. So for the mental is what is known as the spinning wheel or spinning barrel. Is that interfacial layer that separates the outer vortex, where the flow is everywhere upward, from the inner vortex, where the flow is everywhere downward. By upward, we mean that's the region where the axial velocity is everywhere negative in this particular coordinate system, where z is pointing down, and the inner vortex is where the axial velocity u sub z is everywhere positive. And of course, in order to switch from a negative value to a positive value, we have to cross 0. So to find the location of the mental, we simply look at the axial velocities for the complex lamellar and the linear Beltramian models and find the root of those axial velocities where they actually go to 0. And we find, sure enough, 1 over root 2, which is 0.707, and 0.628. And also, sure enough, it turns out that extensive studies carried out at MIT by Professor Joe Smith, who was the department head at MIT for a large number of years, studied, who was an experimentalist, by the way, studied hydrocyclones, and also was able to corroborate the fact that the mental location is rather uniform, averaging either 0.62 or 0.72, which is quite close to the theoretical values that we obtained. And even in the presence of chemical reactions, although the mental deviates a little bit, it remains close to its theoretical mean value. The other characteristic is the location of the peak tangential velocity, what we call a delta sub c, which is the core radius of the forced vortex region that extends from the axis of rotation to the point where the tangential velocity reaches its maximum value. We're also able to capture that theoretically and correlate that to the vortex Reynolds number, which combines the Reynolds number, the Schur number, and the chamber aspect ratio. So not only the body layers are captured at the core and the wall, we also can predict the value of the maximum tangential velocity and the angular speed of the forced vortex core region, which is that solid body column of fluid that spins as a rigid body about the axis of rotation. But really, the most important aspect of what we do, and the reason we have interesting projects with a variety of sponsors, is the fact that we have developed a systematic analysis technology that enables us to take any engine or combustor, no matter how irregular it is, mesh it using an unstructured mesh, run it through our finite volume solver, extract the velocities, pressures, temperatures, densities, all the fluid properties, and then convey those to a structured mesh, then run the structured mesh through our vortoacoustic solver, which works best currently on a structured mesh. And from that, be able to deduce all the frequency spectra and their growth rates. We're able to predict the resonant frequencies, be it longitudinal or transverse. We're able to predict the mode shapes and the acoustic signatures, the waveform structure, and also the growth rates and the stability integrals that help us to pinpoint the sources of instabilities, if any, and the physical sources of those instabilities, being whether they are due to vortex shedding, flow turning, surface work, or viscous effects, etc. We're able to predict those and help in improving the design of those combustors by mitigating those types of instabilities. But it all started in 1995 when I was asked by Orbitech to help them model and analyze the vortex injection hybrid rocket engine, thus leading to our first joint publication, which was a phase 1 final report in 96 for work that we carried out in 1995, leading to an innovative cyclonic hybrid rocket engine. But we also considered other types of engines, including quadrupole vortex-driven engines that have the advantage of scooping the hot combustion products from the core region of the chamber and bringing them in contact with the propellant grain, with the walls, thus increasing the flame temperature at the walls and leading to better regression. And the mechanical analogy here is that of the diamond impregnated tricone heads that are used in the petroleum industry, which are very effective at drilling through the crust of the earth. Other concepts we've worked on include the deeply submerged nozzle in the context of a hybrid rocket chamber that prevents early oxidizer leakage, ensuring that the oxidizer is confined, is shrouded, and prevented from leaking out until full combustion has taken place. We've carried out numerous simulations that help to predict the performance of those engines and their stabilities. We've also looked at unidirectional hybrid vortex engines of the internal burning type and also of the double sandwiched, or what they call vortex pancake type. One of our former team members, Dr. Tim Marquardt, was able to develop a very effective and highly accurate regression rate model that takes into account the effects of swirl on hybrid regression. Tim also worked on an advanced concept of a nuclear thermal propulsion device that was funded by NASA and Jacobs Engineering that led to very nice results. I wish I could share those with you, but also very good stability predictive results as well. Also in the context of solid rocket motors, this goes back to the 80s when Dr. Bob Brown at the Chemical Systems Division of United Technologies noticed that in any type of simulated solid rocket motor, swirl evolved naturally along the axis of the chamber, and yet that phenomenon remained unexplained until, again, one of our unsung heroes, Dr. Ori Cecil now, who recently graduated with a PhD from our department, was able to uncover the mystery of that phenomenon by providing analytical solutions that have been now widely published, receiving the Best Solid Rocket Paper Award of the Year, the most outstanding graduate student in the state of Alabama through the Greater Huntsville section, and also presenting his work and receiving one of the best posters by the College of Engineering. Another student before Ori was Andrew Fisk, who worked for the Air Force, who also received the Best International Paper Award in the Master's Division for his work on a similar problem also leading to a 2017 Journal Fluid Mechanics publication. Another comparable study has to do with an arbitrary cross-section, in this case, a star-shaped grain that we were able to turn into a self-preserving, self-similarity solution that could be solved almost exactly using asymptotic tools and computationally to corroborate the analytical results, also leading to another very nice paper in JFM for a star-shaped grain. We've also analyzed the effects of compressibility, capturing them in a variety of rocketed chambers, leading to, again, papers in the Royal Society and JFM, leading at times to review articles, as shown here in the Royal Society. In short, we were able to develop a mathematical procedure that enables us to take any incompressible profile and find its compressible counterpart that would evolve under high-speed conditions. And that is really significant. Think about it. It doesn't matter whether the flow is 2D or 3D, you were able to find its compressible counterpart, which is very important in the study of high-speed flows. An example is the compressible bidirectional vortex. So that's a three-component profile that includes a axial, a tangential, and a radial velocity component, and we're able to obtain their compressible counterpart. And to circle back to the viscous flow textbook, one of our side projects has been improving the momentum integral approach. And on that count, we've looked at the flow over a flat plate, which has been studied extensively throughout the literature. There have been many models that have been proposed to solve that problem using the momentum integral approach, using different polynomial approximations and leading to different predictions of the boundary layer characteristics, such as the skin friction coefficient, the boundary layer thickness, etc. And we were able to reverse engineer that problem, but by finding a connection, a direct connection between all of these classical coefficients directly with the mean flow function itself that is at the heart of the analysis. Without carrying out any algebra, we can predict all of these coefficients directly from those functions. And by reverse engineering this problem, we were able to compare the accuracy of all these different profiles that are out there that seek to predict the behavior of the exact or true solution to the problem, which for flow over a flat plate is encapsulated in the Blasius solution, which is found numerically. Well, we were able to outperform all of those models out there by finding, first of all, an equally simple fourth order polynomial that outperforms all the models out there by 1 order of magnitude in accuracy, leading to predictions of all the boundary layer characteristics under 0.2% in error, and also a one term using an exponential basis function that is no different from the exact solution. Practically, it carries an L2 error of 10 to the minus 5, which is essentially of the same order of magnitude as the error associated with the Blasius equation itself. So we are very pleased with these results. They've been featured in a special article that was accepted in the Physics of Fluids and designated as a feature article on the cover of the Physics of Fluids website. So with this, I end my presentation. I wanted to give you a quick overview of the different types of projects we work on. They're mostly computational, stability focused, and also theoretical, mathematically focused. And I hope you enjoyed this short presentation. If you have any questions, feel free to reach out to me. And again, thank you very much.